Okay, so this is part three, the last part for day 11 lesson, and I'm going to talk you through how to get through the simulation and kind of go through some examples with Snell's law and how to calculate some ideas. So just to review again, this is basically what we're going to do in the simulation on FET, but again, the angle with which the ray of light is coming in to hit the boundary, that's the angle of incidence. The angle that it reflects off of that boundary back into the same medium, that's called the angle of reflection. And then finally, the angle at which the refracted beam transfers or transmits into the new medium, that's the refracted beam or the angle of refraction, which got a little cut off there. So let me scroll down. Let me also get rid of that. So those are important. And again, all of those things are all measured from the normal, which is perpendicular to the surface. So the protractor that's going to be set up on this simulation, let me get to that. So if, again, you go to FET and then load it up and then go to bending light. That's the simulation you want. Again, it's HTML5, so it'll run on anything. Bending light, that one. Click play. And then you're just going to go to intro because that's all you need. Really, there's not too much difference between the different simulations or the parts of the simulation. You can play around with other things if you like with prisms, but you're going to click on the light to turn it on. You're going to put the protractor right at the normal, so there, and then you're going to just take note of these things. So again, you can move the ray of light and see how it changes the different angles of incidence and reflection and refraction, and you're going to measure those. So if you take a look at going back to here, that's kind of the picture of the simulation. You're going to fill in this table. So we'll maybe do the first trial together. So it says you're going to start with the top material being air and the bottom material being water, which is essentially what you have in the first setup. So this is a picture of the first setup. So the index of refraction for air is 1, so you're going to write that in, and then the index of refraction for water, in this case, is 1.33. So you're going to fill in those up here, so you would just write in 1 for the top index and 1.3, it's supposed to be a 3, and then another 3. Oh, that's really bad. I'll try typing next time. And then you're just going to kind of pick your own incident angle. And you're going to measure the reflected angle and the refracted angle. So I'm just going to go back to the site, and let's just pick an angle that's pretty easy to measure. So we'll start with 30. So if I look at 30 here, I got the line. This is my angle of incidence measured from the 0 to where the beam is. So that's 30. If you look at the, so that should be what I'm going to put in here. So that's 30. Then for the refracted, or I'm sorry, the reflected angle, the angle of the ray that bounces back into the same medium, it's reflected back into the air, that looks like it's also 30. So I'm going to write that down for that table there, 30. And then the refracted angle, the refracted angle is what I need to measure, and this one's a little bit trickier, but if you look at it here, that's 30. That's 10, that's 20, so it's a little bit more than 20, so maybe I'll just estimate it and call it 21 just to give a number. So that's 21 degrees, and these are all degrees. So that's the first trial data, and you're just going to sketch that too. So if you come back down here, I'm going to use the little ruler, but you can kind of, oh, that's way too big, sorry. Let's undo that. So if we just have a ray of light coming in, and we'll say that's 30 degrees. When it bounced out, that was also 30 degrees. And this is just a sketch, so you don't have to get a protractor out or anything. And then the angle that it refracted at was smaller. So again, all of these angles are measured from the normal. So this dotted blue line is the normal, this horizontal line is the boundary. So it's basically the picture that you have on the screen. So that angle is the angle of incidence. This angle here, which would be the same amount, is the reflected angle. And then the refracted angle, this angle here, is the 21 degrees. So so that's what I'm looking for in a picture. You can draw little arrows to indicate which way those different beams are moving to make it a little clearer. But that's all I'm looking for in a sketch. So you'll do that for each of the different trials for each of the different parts. So if you look at the picture of the simulation, so I have that here. So you would do that 2 times for each trial. So trial 1, trial 2 for the first setup, then it asks you to change from the bottom material to glass, from water to glass. You do the same kind of thing, so the numbers change and the angles will change. Then from water going into glass, and then you get to, so the first 3, you just kind of do any angles you want. For the last 3, you have to be a little bit more careful because sometimes you won't get a refracted beam. So let me start out with this one where I just flip the thing. So it's water to air. So it starts out in water and it's going to go into air. So right now this one's fine because I have my incident beam, my reflected beam, and my refracted beam. But if you look, if I move this to a certain angle, oh, what happened? The refracted beam disappeared. So you can't use those. So if you don't get a refracted beam, that's not going to work. So make sure that you have your angle to a point where you can see these 3 rays. If you don't, if you get one that's not showing 3 rays, go back and pick 2 that work. Okay, so for the last 3, you just have to be a little bit careful and make sure you get 3 beams. And that's another physics idea that we may or may not talk about. I usually mention it in class, but we're kind of limiting the stuff that we're learning about, so a little bit more to kind of streamline it. So we'll get back to it. Maybe if you have more questions about it, you could probably look it up on your own if you want. It's called the critical angle and something called total internal reflection. So finally, this is just kind of the rest of the lesson. I'll zip through this pretty quick because you're going to see most of this in your scenarios in the simulation. So we talked about refraction already. It's just the bending of light or a wave as it enters a new medium. The incident angle and the refracted angle. So I didn't draw on the reflected here, but it's still measured from the normal. So the first medium or substance going into the second substance and how it changes. So Snell's law is something called is a relationship between the angle of incidence and the angle of refraction, and then also the medium and the index of refraction in the first medium and the index of refraction in the second medium. So if I scroll down, it has this equation all broken down into all the pieces, so you can read through that and then double check. But you just plug into this, make sure you're in degrees so that it works the right way. If you're in radians, it'll give you some weird answers that you don't want. So let's just go through an example or 2. I have these all worked out, so I will talk through the first one and then I'll just, or maybe the first 2, and then let you kind of figure out the third one, but I'll put the answer up as well so you can check it out. So in this first one, we have a ray of light, which is hitting the boundary, so this big block here is a piece of glass, and it's hitting the boundary at an initial angle of 30 degrees. Then this is so theta 1 here, sorry. I should put that in. So theta 1. And this is index 1, which is air. For the second substance, that's the glass, so that's index 2. And this is theta 2, which is what we're looking for in the first part. So we're going to try to find the angle of refraction and incidence for each side of the glass. So we're going to try to find theta 2. Then with some geometry, this angle, theta 2, is also that angle, so that becomes your new angle of incidence when it hits the second boundary, and then it leaves the glass and goes back into air. So air is actually part 3 as well for the index, and then you just solve for theta 3. So let me go ahead and just plug this into Snell's law, and you guys can see how to kind of follow along and make sure it's working on your calculator too. So I just started out with Snell's law, so n1 sine theta 1 equals n2 sine theta 2, and I plugged in all the numbers I knew. So 1 sine 30, that's the first stuff, equals 1.7 sine of theta 2, which is what we're looking for. So I just do the math in the calculator and let it do the work, and you should get 17.1 degrees. The only thing that's sometimes a little tricky, if you're looking for an angle, you have to hit second sine or shift sine on your calculator. So I just hit second sine and you get this sine to the -1, and then it's 0.5 divided by 1.7. Close that parenthesis, hit equals, and you'll get 17.1 degrees. Something close to that, might go a couple more digits. So that's the angle theta 2 up here. So this angle is theta 2. So the angle got smaller as it looks like in that picture. So it went from 30 to 17 or 17.1. That makes sense because when it goes into a more dense medium, it slows down, and when it slows down, it bends towards the normal. So if the ray of light could just go through and keep going in a straight line, which I'm trying to draw there, but you might miss it. So this would be if it was just going through the same medium or just continuing that straight line. But when it slows down, it bends towards the normal. So this angle bent towards the normal. So that's when it goes into a more dense or slower medium. It travels slower. Then it starts going back and it bends away. So the angle got bigger in this case when it goes from 2 to 3. And it's the same kind of math. So n2 sine theta 2 equals n3 sine theta 3. I plugged in the numbers just like we're given. So 1.7 sine 17.1 was my answer from part A here, or this part. And then the index that it's going into is 1 for error, and then sine of 3, theta 3 is what I'm looking for. So again, I do the same kind of math and solve for theta 3, and I got 30 degrees. So it comes out the same angle that it goes in, which makes sense. So that's the idea. So that's the first one, and just kind of some practice using Snell's law. Similar kind of thing here. So it says using the given information, calculate the optical index of refraction for medium B. So we're looking for basically the index n in this B material or this green material. So that's what I did here. Again, it's just Snell's law. So n1 sine theta 1 equals n2 sine theta 2. So 1 is the index that it starts out in, sine 53 degrees for the angle 1 that it hits the boundary at, because again, we're measuring from the normal to the ray. And then they give you the angle that it bends at is 37 here, and we got to look for n2. So when you do the math, you do 1 sine of 53, and then you would divide by the sine of 37. And I think I skipped a step, but when you put that in your calculator, you should get 1.327. That's the right value. So that's the first part of this problem. Is solving for the angle, solving for the index of refraction. The second part I asked you to do, which I think I do on the quiz as well, is to find the speed of light in that substance. So this goes back to our index of refraction idea. So n equals c divided by v. So that was, I think, in video 1. Sorry, it was all the way back there. But it's also in your notes. So if you go back a couple slides in your notes or look back, you'll find it. So we got n in that substance. So in B, the index is 1.327. The speed of light is 3 times 10 to the 8th. And we're looking for v, so we got to rearrange it and solve for v. So when you do that, you get 2.26 times 10 to the 8th meters per second. Sometimes people have some difficulty with putting the times 10 to the 8th in their calculator. If you're doing that, you can just, if you're having that difficulty, you can just kind of leave the times 10 to the 8th off and just do the 3 divided by 1.327, and that'll get you the 2.26, and then you just add in that, or like after you get that first number, you just add that times 10 to the 8th afterwards. So that's what this note is trying to tell you. So if you're having some difficulty with that, you can use that kind of shortcut, and it'll still give you the right answer. So almost the same kind of thing here. So I'm just going to show you the answers because I know the video is long at this point, so I apologize. But doing Snell's law, you should get that value, and then for finding the speed of light in the lower material, the pink material, very similar to what we just did last time, you should get 1.43 times 10 to the 8th. So that's mostly it on waves and light. So hopefully that helps with that little video. So have a great day, guys. I will see you soon.